Hello again. This is Math 2232, coming to you from the College of DuPage. The title of this lecture is Centers of Mass and First Moments, and more. Please be an attentive learner as you watch this video. Under many circumstances in science and engineering, it is possible to effectively assume that the entire mass of an object is at the center of mass. This simplifies such problems significantly. So, by way of introduction then, we will talk about what happens in a discrete case and generalize it to the continuous case that we're most interested in here. So let's begin talking about moments and centers of mass. So our main objective here is to find a point P on which a thin plate of any given shape, that's the P here, and there's the point, and that's the shape, the point P, if it balances like on the tip of a pencil, that's called the center of mass or center of gravity. Now we're going to consider first one and two dimensions. So let's just look in the one dimension case. Now here, there's your pencil, or we could think about that as a fulcrum on a seesaw. And so what we're really trying to do is, if we're trying to balance the seesaw, what happens, we have mass 1 here and mass 2 here. Their distances d1 and d2 respectively. So here what we're trying to do is manage this is a counterclockwise torque, and this is a clockwise torque. We want to manage the two torques, and in fact that happens when m1 times d1 is equal to m2 times d2. And that's something that actually Archimedes came up with, and that's called the law of the levers. Now suppose the rod lies along the x-axis with m1 at x1 and m2 at x2, and the center of mass is at x bar. So that means that the center of mass is at x bar, so here's x bar. That's where the fulcrum has to be placed to have the balance. So that means that this lever arm from here to here has to be the same as this lever arm. If I set those two equal, I find a formula for the center of mass, and that says that x bar has to be the weighted average of the moments of the masses divided by the mass. Now these two numbers, I already said this, but this number and this number are called moments of the masses m1 and m2 with respect to the origin. And the equation here says that the center of mass, x bar, is obtained by adding the moments of the masses and dividing by the total mass, m1 plus m2. Now we can generalize this to any number of masses, m1, m2, all the way up to mn, located at these points, and we get the same formula. X bar is equal to the summation from I going from 1 to n, mi xi divided by m. And if you add up m being the summation of the masses is the total mass of the system, and the sum of the individual moments is called capital M. And again, these could be pluses and minuses, is called the moment of the system about the origin. This is of the capital M. And so equation 4 could be written as m x bar equals capital M, which says that if the total mass were considered to be concentrated at the center of mass x bar, then the moment would be the same as the moment of the system. This is at the heart of what we're trying to do. Now we're going to talk about in two dimensions. So you see, now we're going to have m1, m2, and m3 located in the xy plane where you have x and y coordinates. Now here, for equilibrium, you really have basically stability happening in two dimensions. One is you would like for it to be in equilibrium with respect to the y-axis, and in equilibrium with respect to the x-axis. Now we do the same kind of thing, except the moments about the y-axis are ending up being these x values, and the moments about the x-axis end up being these y values again. So m sub y is going to be the summation I equal 1 to n of m xi, and the moment of the system about the x-axis is mx, capital MX, is equal to the summation I equals 1 to m of mi yi. So that's what we have. That's what we have going on there. So my measures the tendency of the system to rotate about the y-axis, and mx measures the tendency to rotate about the x-axis. And in a similar argument to what we had before, we have formulas for x bar is equal to the moment about the y-axis divided by the total mass, and y bar is equal to the moment about the x-axis divided by the total mass. And here I've said those things before, I think. Okay, so let's do an example. So you want to find the moments and center of mass of the system of objects, masses 3, 4, and 8, respectively, at points. These, again, both of those are respectively. So you know what to do. Let's see how you did. Okay, well, we find my this way, mx this way, and then I use the formulas to find the coordinates of the center of mass. And so you see here where those masses are located, and that is the center of mass. Now what we're going to do is we're going to consider a flat plate called a lamina. And so here is an example of a lamina. And it is a flat plate, but it is a two-dimensional plate because it's flat. And we've got a region R that's occupied. Now what we're going to do is we're going to simplify this, and we're going to just say, well, what happens if it is a rectangle? Okay, well, if it's a rectangle, what you see is that, well, in fact, let me just derive a few things. So we're going to derive it by rectangle, and then we're going to add the things up. Okay, so first thing we have is called a symmetry principle that says if it's symmetric with respect to line, then the centroid lies on the line. Okay, so that means that if we have, setting up the rectangles like the Riemann sum, that shows that the centroid of the ith approximating rectangle is at its center, which is x bar, and then it is 1/2. And actually this is c sub I because that's the ith rectangle. So that is x bar sub I, again, where it's easy to do the calculation for a rectangle. And this is 1/2 f of x bar sub I. And so the area is going to be the height, which is this, times the width, which is this, times the density. And here we're assuming the density rho is a constant. Later on we can talk about the density not being constant, but that's what we're talking about now. Okay, so that means that the moment about the y-axis of r sub I is going to be this, which is equal to this. And if we add them all together and take the limit, we get that m about the y-axis is equal to rho times the integral from a to b of x f of x dx. Make sure you understand this derivation. In a similar fashion, we can find out that the moment about the x-axis of each rectangle is this. Now notice the formula is different. This is going to be rho times 1/2 f at x bar sub I squared delta x. And if we take the limit of those, we find that the moment about the x-axis is rho, the integral from a to b, 1/2, this is f of x whole squared dx. And the mass is always going to be, because the density is mass per unit area, it's going to be rho times the area. And so we have these formulas, and notice that the rho's will cancel out because they're constants. And in summary, here's the formulas. that we have. They should be committed to memory because you're going to have to use them, so make sure you're writing them down. And here's a problem to test your understanding. Find the center of mass of a semicircular plate of radius r. You know what to do. Let's see how you did. Well, first of all, the equation of a semicircle of radius r centered at the origin, it might as well be centered at the origin, is f of x is equal to the square root of r squared minus x squared. So then y bar is equal to 1 over a, the integral from minus r to r, 1/2 f of x whole squared dx. Now when we square that, we're going to get rid of the square root, and when we integrate an even function, because this is just r squared, across minus r to r, that's the same thing as twice the integral from 0 to r, and so the 2's will cancel, and that's what we do. This 2 here is actually that 2. And so this is an easy integral to compute, but make sure that you can follow the computation. We add 1 to the exponent, divide by the new exponent. Use a fundamental theorem of calculus. We plug it in, we simplify our answer, and we get 4r over 3 pi. And here is a picture of what we did. Here's another problem for you. Find the centroid of the region bounded by, these are trig things, by the curves y equal cosine x, y equals 0, x equals 0, and x equal pi over 2. You know what to do. Let's see how you did. Okay, first we find the area. That is this integral. Here's the picture that we have. So you're going to integrate for the area from 0 to pi over 2 cosine of x dx. I compute that and I find the area is 1. So x bar, again I use my formula. Now this is going to be x cosine x dx. We have to use integration by parts. That's a good review of that. Make sure you follow these calculations. So we get pi over 2 minus 1. Y bar is equal to 1/2. This is the integral from 0 to pi over 2. That is cosine squared of x. Now again, to integrate this, we have to use the double angle formula. Or maybe it's the half angle formula, I never really know. And we get pi over 8. And so the centroid is pi over 2 minus 1, comma, pi over 8. And here is the picture. Now, if the region lies between two curves, y equals f of x and y equals g of x, where f is the one that's on top, then the same sort of argument that we did before gives us a definition for the centroid here, where x bar is equal to, this is x times the difference, dx, divided by 1 over a, and y bar is 1 over a times, and this is 1/2, the one on top squared minus the one on the bottom squared dx. Similar kinds of arguments. You want to think through these. So that means we can actually have a lamina that looks like this. You have one curve on top and one curve on bottom, but here are formulas that you have. Let's use those formulas to do a problem. Find the centroid of the region bounded by the line y equal x and the parabola y is equal to x squared. You know what to do. Let's see how you did. Okay, this is the picture that we had before. We're going to calculate the area first. So the area is the integral of, the one that's on top is the line, the one that's on the bottom is the parabola. We do the calculation and we get that that is 1 over 6. So that is what A is. And then we're going to use the formulas that we had. So x bar is equal to this, is equal to this. Make sure you follow the calculations and you get 1/2. Y bar is equal to 1 over 6, and here's what we have, and we get that. So the answer is x bar is 1/2 and 2 over 5, and you can see that that's where the center of mass would be. Now, it turns out that there's two very interesting theorems attributed to a Egyptian mathematician, Papacy, and this was long before calculus was invented. Our proofs are going to be using calculus, but you can use this theorem and realize that this guy figured these out without calculus. Okay, so here's what the theorem of Papacy states here, at least one of the theorems of Papacy. Let script R be a plane region that lies entirely on one side of a line L. If script R is rotated about L, then the volume, that's the volume we talked about, this is the volume of revolution of the resulting solid, is the product of the area, A, and the distance D traveled by the centroid of R. Now here's the proof. And we know from our previous work that, and again, we know that the volume is going to be equal to the integral from, and this is the shell method, from A to B of 2 pi x times the difference between the top function and the bottom function. Now, in our case, then what happens is that this is 2 pi, but this is just x bar times the area of A. And when we simplify that, that is going to be A times, and this is the distance that the centroid travels as it is rotated around AD. And so you see, we've proven this theorem. He had another theorem too that really had to do with the surface area. And so the surface area of revolution formed by rotating the boundary curve C about the axis, and the surface area of F is equal to the length of C, the length of the curve, multiplied by 2 pi, and C star is the distance from the center of mass for A and C respectively. Okay, so there are two of those theorems, and in fact, the proof of the area formula, this is our formula for surface area, and this is the length of the curve. So that means that the area, the surface area of F, the revolution, is given by this. But the y-coordinate for the centroid is C star times this is equal to that. So you see that if we substitute this into the first equation, we have the second formula. All right, let's have you do something here. A torus is formed by rotating a circle of radius r about a line in the plane of the circle that is at a distance of capital R, that's bigger than the radius of the circle, from the center of the circle. Find the volume of the torus. You know what to do. Let's see how you did. Well, if we're just using the theorem, we know that this area is pi r squared. We're using Papacy's theorem. And if we go around, there's the center of mass, which is the center of the circle. It goes around there, so that's a circle of radius capital R. So that is the area times the distance that the centroid travels as it goes around. And so this is 2 pi squared r little r squared times capital R. And in fact, you could also find the surface area of this. You know what to do. Let's see how you did. If you use Papacy, this is the area, and that's the distance that you go around, and this is the surface area. Now, it is quite instructive for a student to derive this without Papacy's theorem, and you do have the tools, so think about doing this. But let's do one more example. A regular hexagon of side A is rotated about one of its sides. Find the volume of the solid of revolution. You can do this without Papacy's theorem, but I'm going to ask you to use Papacy's theorem here. That's my recommendation. It's actually easier. You know what to do. Let's see how you did. So here's the hexagon, and we're rotating about one of its edges. So it's this one that we're choosing. Okay, so this is a hexagon. You know a lot about hexagons. You know that from the geometry, you know a lot about the angles and the central angles, and it's a regular hexagon. So the central angles for each side subtending are going to be 60 degrees because there's a total of 360. They're all equal, so 360 divided by 6 is 60. And what you're doing is here you're going to find the distance from the center of a mass, which is the center, and so that's going to be here. So that's kind of the geometry that we're talking about, and each side is A. Okay, so given the side of the hexagon is A, we can easily find the apothem length. This is actually called the apothem. You don't have to know the name, but that's the distance you need to know. So M is equal to A over 2 times the cotangent of 30 degrees. That's going to be A over the square root of 3 over 2. So the distance traveled by the center, the centroid, when rotating the hexagon is 2 pi m, which is 2 pi times this, which is pi a times the square root of 3. So that is the distance, pi a times the square root of 3. Now the area of a hexagon, you can compute this as well. You can find the area of the 6 triangles and add them together, and you get that the total area is a squared 3 root 3 over 2. So using the theorem about the volume, it is A times D. I multiply those two numbers and I get 9 pi A cubed over 2. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.